nanohub.org.
Online simulation, and more for nanotechnology.
Today's topic is wave-based characterization. It's session number 10. I believe Dr. Gazarinoff will be batting leadoff. He is at Portland Community College in Portland, Oregon.
So good morning, everyone, and good afternoon to those on the East Coast. Welcome to the first part of our seminar today. I'm going to be talking about X-ray diffraction. I'm Peter Kazarinoff. I'm faculty in engineering at Portland Community College. I teach engineering transfer students as well as two-year technician engineers. I'm also the co-PI of MinTech, the National Center for Micro Nanotechnician Education, and I'm one of the editors, along with Netta and Oskar, of the Journal of Advanced Technological Education. I'm also the host of the Talking Technicians podcast, and you can get in touch with me by emailing me at peter.kazarinoff@pcc.edu. As Bob mentioned, this is part of our Nano Educators topical seminar series. Last week was on optical lithography, and this week we're talking about wave-based characterization. So before I get started talking about XRD, I just want to do a quick review of fabrication and characterization in micro and nanotechnology. So fabrication and characterization have specific meanings in micro and nanotechnology. Fabrication means making something, and that could be adding a material, removing a material, shaping a material, or modifying a material. And fabrication examples include things like lithography, etching, and deposition. Characterization in micro nanotechnology, that means looking at something. So that could be analyzing its shape, looking at its structure, maybe its chemical composition or its properties. And examples of characterization include microscopy and spectroscopy. The wave-based characterization techniques that we're going to look at today are part of a subset of micro and nano characterization. So before I go on and talk about XRD in particular, I've got a Jamboard, and I'm going to stop my PowerPoint share, and I'll hop into that Jamboard and just quickly show you how those works. So on my screen share right now, you should see the Jamboard, and you'll get there by clicking the link in the chat. On the left-hand side, these are all of the buttons that you can add things to the Jamboard with. So this kind of middle one that says sticky note, if you click that, then you can write a new sticky note of a piece of characterization that you've used before. So for instance, I've done some scanning electron microscopy. So I'm going to put SEM, and if you want, you can change your note color. And then once you add your note, then you can move your note. So we'll spend a minute or two. I just want to see what kind of characterization techniques people on the seminar have used. I'm going to stick a couple more in for me. So we've got a couple things up on the Jamboard. So if you're able, I'm going to highlight a couple of these things. And then if you're able, just pop your mic on and let everybody know in a sentence or two what that thing is. So who stuck DLS, dynamic light scattering, up there?
That would be me.
Yeah, Oskar, just in a sentence or two, what's DLS, dynamic light scattering?
Yeah, so we were synthesizing nanoparticles with the students, and we were looking at the size distributions. It's another light-based characterization method that interacts with the nanoparticles, and it's actually a very detailed analysis and can give you a very accurate distribution of the nanoparticle size. So it can tell you like you have 35 nanometers and also like 70 nanometers at the same time.
Thanks. How about ellipsometry? Who put ellipsometry up there? Are you willing to turn your mic on?
That's me again.
That was you too? Okay, yeah, in a sentence or two, what's ellipsometry?
Very shortly, we're just coating the silicon or growing some oxides and different oxides, not just silicon dioxide, and looking at the thickness of the silicon dioxide and the other aluminum oxide or so by using laser light and trying to get the thickness of that bulk material.
And often used in things like semiconductor wafers, right? Who put in XPS?
That was me.
Yeah, what's XPS? What does it stand for? And what is it?
X-ray photoelectron spectroscopy. It's a surface analysis technique. So you can use X-rays to you hit a surface with X-rays, and photoelectrons are ejected, and you can measure the kinetic energy of those photoelectrons to learn about the elemental composition of the surface, as well as what binding environment or oxidation state those elements are in. And it's really useful for analyzing the surface of a material.
And what kind of samples does XPS get run on, or that you've run it on?
It's an ultra high vacuum technique. So basically the only requirement is that the samples have to be able to withstand that environment. But we can look at thin films of nanoparticles. We've looked at polymer tubing materials, other parts of metal bulk parts, pretty much anything. We've looked at a lot of different things.
Cool. So thanks so much for sharing all those different characterization techniques. And I'm sorry we didn't get a chance to go through all of them, but the one that I want to talk about now is going to be XRD, or X-ray diffraction. So a bunch of the characterization techniques that were on that Jamboard, those were wave-based characterization techniques. And you can divide wave-based characterization techniques in a bunch of different categories. A category that I've chosen here is based either on the wave type. So that could be an electromagnetic wave, like a light wave in DLS, or an X-ray in XRD. It could be a sound wave, like an ultrasound. Or if you could consider particle type waves, that could be things like electron beam techniques. And then you could also divide wave-based characterization up into a category of wave coverage. So there's some that are ensemble techniques. I would call XRD and DLS is like an ensemble technique. But there are also scanning techniques where you move like a beam across the surface, looking at different parts of the surface at a time. And then there are other techniques, which could be pulse techniques, where the wave-based characterization is turning on and off. So the specific characterization technique I'm going to talk about is X-ray diffraction, or XRD. X-ray diffraction is done with an instrument called an X-ray diffractometer, and it's usually accomplished on crystalline samples, and these could be solid samples, and often they are powders. XRD can give you composition and structural analysis information, and it's a sort of pseudo non-destructive process, and it's relatively fast. You can get data in minutes. I put non-destructive in quotes because often XRD is done on powdered samples, so you'd have to grind your sample in order to run it. But you can also do XRD on solid samples. Some samples, though, the X-ray radiation will introduce a change in the sample. So it's not exactly completely non-destructive. This is an image of an X-ray diffractometer. This is Bruker's D8. It's one of the more common X-ray diffractometers that are in research labs. And in XRD, an X-ray is generated from an X-ray source. Those X-rays interact with a sample, and then the diffracted X-rays are collected by a detector. And we'll talk about each of those different parts of the X-ray diffractometer next. X-rays are electromagnetic radiation, and they are in the X-ray wavelength, and that's wavelengths from around 0.1 angstroms to about 100 angstroms, an angstrom being 10 to the minus 10 meters. And the X-ray wavelength is around the same size scale as atomic arrangements. So XRD can give us information both about chemical composition, but also about atomic arrangements, things like lattice parameters or crystal structure type. An X-ray diffractometer that gives us our XRD scans is made up of a couple different parts. On the left-hand side, you can see the X-ray source. X-rays are emitted from the source and then hit the sample, which sit on a sample stage. And the sample stages can be heated. They could be hanging sort of in midair, or they could be organized in a different way. There is a detector that counts the X-rays that are diffracted from the sample. And the detector, the sample stage, and the X-ray source are connected to something which is called a goniometer, which moves the angles of those three things relative to each other. Since an X-ray diffractometer produces X-rays, there is shielding around the instrument to prevent technicians that operate these instruments from being exposed to X-rays. The X-ray sources in X-ray diffractometers are generated by typically hot filaments, which create electrons, and then an electromagnetic field accelerate those electrons to a metal anode target. When the electrons hit that target, they emit X-rays, and typical anode materials include copper, that's one of the most common ones, but also chromium, molybdenum, cobalt, iron, and manganese. There are also typically slits and windows used on the X-ray sources to control the X-ray beam, either to control the wavelengths that come out or to control the width of the beam. And on the right-hand side, you can see an image of one of these X-ray sources from a company called Malvern. The goniometer is a mechanical device that measures angles. And in XRD, the angle of the X-ray source and the angle of the detector is changed relative to the sample stage. Some goniometers keep either the X-ray source or the detector static and move the sample stage and then the other piece of equipment, but many XRD diffractometers move the X-ray source and move the detector. As the goniometer rotates through angles, the detector records diffracted X-rays. The X-ray detector is the part of the diffractometer that detects the X-rays, and the detector measures X-ray counts or X-ray intensity. Some X-ray detectors merely detect the quantity or intensity of X-rays, and other X-ray detectors can measure in 1D or even 2D for specialized measurements. I teach technicians at Portland Community College, and so for thinking about teaching technicians about XRD, the kind of things that they might do with it include maintenance of the instruments. They might prepare samples, like I'll show you in a sec. They might mount samples into the instrument. They might run the samples. They might swap out X-ray sources so that you've got a different metal and emit different X-ray wavelengths. They might confirm safe operation to make sure that the shielding is in place and that no X-rays are being emitted from the instrument. And they might also do calibration on the X-ray diffractometer. So next, we're going to talk about how an XRD measurement is actually accomplished. And I've got a couple of short videos to show you. Since we're in a virtual setting, I can't introduce you to an actual lab that shows an X-ray diffractometer, but I've got a couple of videos to show you about how it works. So this first video is going to show how to prepare a sample. And this might be something that a technician would do to a sample that they're brought before they put it in the X-ray diffractometer. And in this video, you'll hear from Nicole Wunderling, who is at Penn State, and she's going to talk about how to prepare an X-ray sample.
I'd like to demonstrate for you the way we prepare a sample for powder X-ray diffraction using a top or front-loaded mount. The type of sample holder that I'm going to use is made from a piece of single crystal silicon that's been cut at a specific angle so that it gives us nearly no background and certainly no diffraction peaks in our diffraction pattern. You'll notice that it has a cavity in the center that's about 0.5 millimeter thick and about 35 millimeters in diameter. What I'm going to do is take a little bit of powdered material This has already been roughly ground. I'm going to grind it just a little bit more using a mortar and pestle. Just to take out any sort of agglomeration that might be present. For the purpose of this analysis, I would like my particle size to be on the order of about 40 to 45 micron. Okay. So I'm going to take a little bit of that powder and I'm going to put it in the cavity. I want a little bit more than it takes to fill the cavity. And then I'm going to take my glass slide and I'm going to use the edge of the slide to move the sample into the center of the cavity. And then I'm going to use the flat part of the slide to level this out, with the goal being to make the surface of my powder level with the surface of the sample holder. This is actually a fairly important requirement when we're prepping any sample for powder X-ray diffraction. The height of the sample is very critical to the quality of the data that you collect. And so we try to do a very nice job of making sure that that is the case.
So in that video, what you saw was Nicole preparing a sample for the X-ray diffractometer. So next, we're going to look at how do you actually mount a sample into an X-ray diffractometer. And again, this is going to be Nicole from Penn State.
I'd like to show you now the way that we take the top-filled mount and mount it into the diffractometer. This is a fairly simple process. Right now I have installed on our instrument what we call the flat holder or the flat sample stage. Very simple device. It's basically just a little clip that's spring-loaded. And I'm going to take my sample that I prepared and insert this by pulling down on the clip and putting the sample holder in at an angle like so. We want to leave on this particular instrument a slight gap between the back of the holder and the sample that's maybe 5 to 10 millimeters in depth.
So in that video, what you could see was Nicole mounting her sample in the X-ray diffractometer. Now, the last video that we're going to take a look at for XRD is going to come from Tuesday Kirkendall, who is a technician at the University of Washington.
For X-ray diffractometry, powder diffraction, it is important to have a well-defined polycrystalline material. And the individual particle sizes of your material should be below 45 microns. You need enough to fill one of these wells, and it should be packed in. And what is important is to have enough of each individual crystallite plane so that when the beam hits it at a particular angle, Bragg's equation is satisfied and you get a peak. This is sort of a statistics issue, and so you want to make sure you have plenty of sample so that all those planes are represented.
So what Tuesday was mentioning was the kind of data that you can get out of an X-ray diffractometer. And here's an example of alumina, Al2O3 nanoparticles. And aluminum oxide is one of the materials which is often used as a standard in XRD measurements. So that concludes my introduction to X-ray diffraction. Think about how can you use XRD in your classroom?